Okay, in this section we're introducing the notation for an indefinite integral. However, I don't quite follow the way the author is doing this. I would normally explain the symbolism here in terms of a definite integral. So let me explain it the way I think I can best present it. And between what I say and what the author says, you can take your pick on how you want to approach this. This section is about the indefinite integral, and the following section is going to be about a definite integral. And I think we need a little bit of both to get this. This kind of a problem here is actually introduced in the problems for this section. So it's not that far out of line. So let me just explain it this way. If you want to find the area under a curve, we can approximate it by taking a bunch of strips like this. And whether we take the trapezoids to try and get a little bit closer to the curve, or whether we just take rectangles in what's called a Riemann sum, it's a very similar approach. And as we take the limit, as our little delta x's here go to 0, it really doesn't matter which way we do it. If we're going to actually go to the limit, it should be the same limit either way. But let's look at where the notation for the integral comes from. This is an integral notation down here, and it's used for both definite and indefinite integrals with just a slight variation. So look at one of these strips, okay, any one of these strips. Notice the height of this strip is given by f of x for that particular x. So take the midpoint here, for instance. For this particular x, f of x is the height, and delta x is the width. And so f of x times delta x is the area of that particular strip. And then we take the Greek letter sigma, which, by the way, is the Greek version of the letter S for sum. And so we're going to sum up all of these strips. F of x times delta x gives us one strip. The sum of all the f of x delta x's ends up being the sum of all these strips. And so that would be an approximation to the area here. If we take the limit as delta x approaches 0, then this becomes better and better. It's a better approximation the thinner we make the strips. The point here is that notice that the notation for an integral follows directly from this notation for a Riemann sum. The f of x is the same, and instead of delta x, we're going to go to dx. So we're basically going back to the idea of shrinking our deltas down towards infinitesimal size, and then we'll just call them dx. And so f of x dx would be the area of a very, very, very thin strip. And the sum, instead of using the Greek version of an S for sum, we go back to an English version of an S for a sum, except it's elongated like this because we're going to put more notation on it a little bit down the line. So this is an integral symbol, and just think of it as an S in the same sense that this is an S, and it stands for the sum. But this time it's an infinite sum of a bunch of infinitesimal quantities. Okay, so this is the same as the limit of the sum of these finite width strips. When we shrink them down to where they're infinitesimally thin strips and lots of them, we put them in this form. Okay, so that's where it comes from. Now the amazing thing, which is what we're going to explore later in this chapter, is why the antiderivative is the thing that gives us this area, but it is. Okay, so for right now, let's just take it on faith for a few more sections here, that this area is given by the antiderivative of the function. Okay, now whether we take the antiderivative and add a constant, or whether we evaluate the antiderivative at a starting and ending point, like we do in a definite integral, that's what makes the difference between the definite and the indefinite integral. The notation, however, arises, I think, very naturally out of this kind of notation. Okay, so we now have a formal definition of an indefinite integral. So if g of x is the indefinite integral of f of x with respect to x, then the derivative of g is going to be f. Okay, so basically taking the integral of this function or taking the derivative of this function, these are inverse operations of each other. Now, the text lists two properties of integrals that are convenient to use, and it actually goes through a proof of one of them and leaves another proof for the problems. What I'm about to show you is not a formal proof, really, but it's a way of making sense of this notation. Let's compare these integrals with Riemann sum notation. In other words, let's take the summation of k times f of x times delta x. So this is like a bunch of terms added together, and each of them have a common factor. You know from the distributive law, or the extension of the distributive law to many terms, you can pull out the common factor to the outside of the sum. Okay, so this is going to be equal to k times the sum of what's left, which is f of x times delta x. If you take the limits of these, notice that the limit of this expression would be this, and the limit of a constant times some function is the constant times the limit. So I can pull the k to the outside of the limiting process, and so it shows up on the outside of this integral. Okay, so that's one way to see this. Let's do the same thing for this notation. Notice that if I have an integral that involves a sum of several terms, I can break it up term by term, because I could do the same thing if these were sums. The sum of f of x plus g of x plus h of x, for instance. In other words, it's not intending to just be three terms, but however many terms we have to add, times delta x. I could use the distributive law, and so this would be the sum of f of x times delta x plus g of x times delta x plus h of x times delta x. Okay? And the sum of this plus 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 this, etc. is the same as the sum of all of these plus the sum of all of these plus the sum of all of these. And then when I take the limit of a sum is the sum of the limits, and then these all go to the integral form. Okay? When you get to this situation in the problem section, see if you can set up this proof in parallel with the way the earlier theorem was proved in the book. Okay, let's just go through the examples given in the book and do these indefinite integrals, and remember that the indefinite integral is equivalent to saying an antiderivative. So we're looking for what function has this as its derivative. Okay, so it's going to be something like the sine. And so if I start with that and say if I take the derivative of this, the derivative of the sine is the cosine, but the chain rule, I would bring out a 5. And notice that 5 happens to already be there, so we're home free. So that's what we need. So this integral would be the sine of 5x plus 3. Don't forget to say plus a constant. Example 2, we have 7x plus 4 to the 9th. What is the antiderivative? Well, it's going to have to look something like 7x plus 4 to the 10th. If I take the derivative of this function, it's going to give me 10 times 7x plus 4 to the 9th. And I'm also going to have a 7 that comes out from the chain rule. So that, in other words, is 70 times 7x plus 4 to the 9th. That's not what we're looking for. So what I need to say is 1/70th of 7x plus 4 to the 10th, because that will then cancel this extra stuff we have here, and that'll give us what we're looking for. So that's going to be the antiderivative. It's 1/70th of 7x plus 4 to the 10th plus a constant. How about an exponential? Well, the antiderivative is going to have to look like the exponential itself. But if I take the derivative of this function, it's going to be e to the minus 2x times a minus 2. And so I need to cancel that out. So I go minus 1 over 2 e to the minus 2x, because now when I take the derivative of this, the minus 2 cancels the minus a half to produce the result we want. So this is going to be equal to minus 1/2 e to the minus 2x plus a constant. How about this, where it's a base other than e? Well, we can always convert this to a base e exponential. Okay, so this is the same as the integral of e to the x log 5, because e to the x log 5 is the same as 5 to the x. So the integral of this would be e to the x log 5 times, it's going to bring out an extra log 5. Okay, so we want to cancel that out, and so the function we're really looking for is e to the x log 5, and 1 over the log 5 has to be out here so that when I bring it out it cancels. And then I can rewrite this as 1 over log 5, and this is simply 5 to the x. So the integral here is equal to 1 over the log of 5 times 5 to the x plus a constant. So this is an exercise in reasoning backwards. You say, here is a function, what other function has this as its derivative? And then if you start by approximating such a function, doing the derivative and see what extra stuff comes out, and then what do you have to do to cancel it. And so then you can construct this resulting integral, and don't forget to add your constant. As long as we're talking about indefinite integrals, this is important. Why is that? It's because if I take the derivative of this whole thing, the derivative of a constant is 0, I'm going to get the same result as if I did this by itself. So this function, or any other function that has a constant added on, is the set of all the functions that have this as its derivative. So this is the most general way to write the antiderivative. Okay, try some problems on your own.